So let's look at sample number 3, file, open, go up a level, convex corner, there. Before we get to that though, when I was started to run that thing slowly, I was going to say it's about as interesting as watching paint dry. And this is actually a PFC 2D simulation of effectively watching paint dry. This is a bonded assembly and there's suction between these things and we're changing the saturation. And now we're going to watch bonds break and we're going to look at the displacement field. And this is going to cause shrinkage cracking. And you're going to get this sort of hexagonal-like packing as this thing responds to the change of saturation. What's happening is there's a change in suction between the grains, and then this is naturally forming this this shape. I think that's kind of cool. So it's because of this thing is shrinking. It's shrinking and it's actually fixed on the outer boundaries. So as that thing shrinks, it's going to naturally want to break up into this pattern. You may have seen like salt flats, like old lakes, and they break up into this hexagonal pattern due to the shrinkage cracking on the surface. So enough said. Okay, single ball rolling or sliding around a corner. So let's run this. Here's the view. There's my system. Now let's look at what we had for this thing. So this thing has 0 friction on it. Okay, we gave it a density, we gave it a low damping. We're going to put that orientation tracking stripe on. We're making a wall. This time we're using the vertices keyword. So we're actually giving it the location here, here, here. That's making the wall with the 3 vertices. Let's turn on the orientation tracking. And there's low friction on this. And now if I cycle, it's bouncing a little bit, damping out. And now, and that blue thing is the contact force. Make sense? And it's not spinning because there's no friction. So if we give friction, let's first still keep no friction, but let's put heavier damping on, 0.7. And now if we run it, it's effectively sliding. It's like just vibrating. You can see that contact force. And so it's basically sliding down that thing with a little bit of bumpiness as it's going. And because it's frictionless, it's not spinning. And you're going to see it's going to go around the corner. The contact force now is going to change its orientation. Notice the contact force is always directed toward the center. There's no shear component. And so this essentially was sliding around, sliding down. If we give it a 0.5 friction coefficient, it's effectively going to roll. Can you see it beginning to roll? Yeah, because I'm updating the plot. I think I'm updating it almost every step. But now it's going to roll down the corner. Okay. The only thing else I want to show. Yeah, and of course, if I reduce damping to 0, because it's up here, it's going to start bouncing. And let's do options, view, update. Update interval is 1, right? That's why it's going so slow. Now watch, it should start bouncing. Boom, and there it's going to bounce down and it's going to spin at the same time, right? So again, illustrating the general idea, illustrating that walls can have any shape because you can specify vertices. Okay, you don't have to create boxes and just things like that. Okay, now let's look at the other case. Let's remove from, now let's look at case 4, new data file, go up. What? Let's see, what did it just say to me? Let's see. There, I must have clicked on the wrong one. Here's a single ball rolling or sliding into a concave corner. So this guy has friction. There we go. And gravity is on. So if I run this one, and contact forces are blue, it's going to bounce around a little bit. And actually, I may not have damping on in this case. Let's take a look at what I've got. Yeah, there's no damping on this. So this thing, there's no damping, but it seems to be losing energy. Why? Why? Now, why else can a system lose energy? The key element here is that I have friction in the model. Okay. So as that thing bounces, there is frictional sliding occurring. And frictional sliding, when it's actually sliding, it's dissipating energy. Okay. So this, just the friction alone will dissipate some energy. It takes a long time to dissipate the energy. And what it's doing now is there's essentially two springs there now. And those springs, it's basically vibrating back and forth where the springs are just in the normal direction. And so it's basically the force is staying the same, but it's a little bit of a vibration because there's no damping in here and there's no frictional sliding anymore. So it's got to, that's the best it can do. And it's rattling around. If I say ball attribute damp 0.7 and continue to cycle it, boom, it's done. It's not moving anymore because damping took out that vibration that was going on. We could also, instead of using that local damping, we can activate the dash pots. And so this is a fraction of critical damping. It's called. It basically means that if it were to bounce once, it would take 50% of its energy out every time the dash pot gets hit. So now if I run it, oh, what happened? Layout wide. There. And so there, it stopped bouncing. Now it's just rolling because the dash pot is taking out the energy. The dash pot and the friction in this case. So now it should just bounce a little bit. Oh, look at that, rolled up the other side. And it's going to it's going to roll back. You get the idea, right? You could play with this. Oh, I've never heard that. This is kind of cool because you're seeing it, because you're running it, you're updating the plot so often. Yeah, look at that. Yeah, that's pretty cool. Okay. Shift escape. Done. And the last thing, just because it's fun, we're going to have no viscous dash pot, no damping, and no friction. And so now it's just going to bounce around. And I'm going to change the update interval to be 10. Options, plot, update. Let's do 20. And continue to cycle. And so there we go. And whoa, it's almost, and if it is unlucky enough to not exactly conserve energy on one of those collisions, it's potentially, if you run this long enough, it's going to bounce and it's going to fall off the edge because gravity's on. Of course, it's not doing it for me right now, but oh, it almost did. But you get the idea. Okay. All right. There's the basic examples with one particle.